Alright, so in today's problem, we are going to look at the problem next permutation. How do we generate the next permutation given a sequence that we already have? So if our sequence is 1, 2, and 3, the next permutation in that sequence is going to be 1, 3, and 2. If I have 3, 2, 1 as my permutation that I'm given, the next permutation in the sequence is the first permutation. Because this is the last permutation of the numbers 1, 2, and 3, this is the last permutation. So we just return the empty array. There is no next permutation. 1, 5, and 2. What is the next permutation? The next permutation is 2, 1, 5. When you're looking at these, you might not see a pattern, and I myself, I do not see a pattern. But we do not see a pattern until we understand how permutations are built. Alright, so we have two choices to this problem. We can generate every single permutation until we hit the permutation we are given. And then we go one step forward. That will give us the next permutation. The problem with that approach is we're going to be doing factorial time work, and factorial times n, whatever work we're doing in our base case or our individual calls, but we are going to go through, at worst, n factorial permutations if we're given the last permutation, and this is a very expensive way to go about things. The point of this problem is not to have you brute force it like this. The point of the problem is to see whether you really know how a permutation is built and whether you can do an in-depth case analysis. If you have not seen my video on building permutations and permuting a string, I highly recommend that because that will help you a lot with understanding what goes on here. But let's investigate. Now, let's start connecting the dots and see how is a permutation built. So, if we're given 1, 2, and 3, what we need to do is we need 3 slots. The point of a permutation is to exhaust the possibilities of placing each one of these letters in a slot and then recursing and then placing the rest of the numbers. So here's an example. At the first position, we have the choice of placing the 1, the 2, or the 3. When we're doing it like this, temporal order gets precedence. So we're going to place the first item, the least item, which is 1. So I want you to notice something. 1 is not in our possibility space. We are at the second slot. We only have 2 choices. We have 2 slots, we have 2 choices, and at this second slot, we can either put a 2 or a 3. We can either put a 2 or a 3. Notice that. So what you see here is we planted a 1, and that's exactly where our permutation stands. In its state right now, they decided to plant a 1. And notice, they decided to plant a 2. So at this position, we either could plant the 2 or 3. The decision was made by this person, or however this permutation panned out, to place the 2. At this position, at this state, it holds a state. It is currently exploring the number of ways it can place 2 and then recurse. We place the 2 and we explore all possibilities. And then after we place the 2, our decision space is down to 3. Now all we can place here is a 3. Let's place the 3. And now we have exhausted our decision space. At this slot, all we could place is the 3. So now we ask ourselves the question. We ask ourselves, what is the next permutation to 1, 2, 3? Now, do you notice how we understand more about the problem? We understand more about the state that the permutation we are sitting in came from. Where did it derive from? What state is this slot in? This slot is in the state of exploring the placement of 2. Notice that we have exhausted all the placements. All we could place here is 3. We've done 3. So what we need to do to find the next permutation is backtrack 1. Okay, we backtracked 1, and again we're going to get to the core algorithm, but I just need you to understand this walkthrough. So we got through the 3, and now this slot is empty. 3 is back in the decision space. And notice, we planted on 2, we explored all of the possibilities that 2's placement had to offer, which was placing a 3 here, and now 2 has exhausted itself. And the 2 returns to the decision space. So now we can use either 2 or 3. At this position, the next thing to place is going to be a 3. Before it was 2. 2 did all of its exploring. This was on its last permutation, and now we place the 3. And now notice, 3 is not in our decision space anymore, and now all we can place here is 2. And so now, 1, 3, and 2. So what is the overarching state? The overarching state is we planted a 1. What else could we have planted here? We could have planted 2 or 3. So all the while we're doing our exploring over here, we are doing it off of the planting 1. While we're doing our exploring here, we're doing it off the planting 3. While we're exploring here, we're doing our planting off of 2. It is all about planting and exploring possibilities. So this is the next permutation. So let me ask you, what would the permutation after this be? So what we notice is that a section that is decreasing has exhausted itself and reached its last placement. If we tried to find the next permutation, what we would do is we would need to see where we need to backtrack. So what we do is, we notice the 2 has exhausted all of the possibilities. So we need to erase 2 and return it to the pool. And notice we have no more things to explore at the second slot. We've tried the 2, we've tried the 3. So we erase the 3. And so now we have explored all of the possibilities with 1 rooted in the first slot. Now what is the next item to get rooted? 2 is the next item to get the rooting. And now our decision space has adjusted itself. 2 gets the planting. We're now exploring on 2. And now we have 2 choices for the second placement. We can place the 1 or the 3. And now we choose precedence on the lesser item, so 1 gets the placement. And then all we can put in the last slot is 3. That's all we have left. So this is the next permutation. This is the permutation after the permutation we just made. So I want you to start noticing a pattern. What we're doing is we're looking for a strictly decreasing section because that is the section that has exhausted itself. This has exhausted itself, so this would get erased. So the element before the strictly decreasing section is the element that still has options to explore. So now the next option would be to explore the 3. And then so on. So what we notice is the item right before a strictly decreasing section is the item of interest. That is what we need to do our modulation on in order to advance us to the next permutation because the strictly decreasing section has exhausted itself. The item before that section has items that it can swap between. It still has more choices for its slot. So let's look at a concrete example to see this pattern. So this is a very tricky case analysis problem. This is not something where you just instantly know the answer. And I need you to make a few intellectual jumps here so that you can really let this sink in. So what we just noticed is each of the decisions are plantings. So imagine I am given this permutation. We'll see why these are important. But notice, this person said, let me plant 6. It goes out of our decision space. They said, let me plant 2. It goes out of our decision space. They said, let me plant 1. And then 1 disappeared from the decision space. But notice here, this item is before a strictly decreasing section. Remember, we just established a strictly decreasing section is on its last permutation. If this section is on its last permutation, what do we need to modulate? We need to modulate what is right before that strictly decreasing section. Why? So when we are at slot number 3, we have these choices. We already expressed all of 0's decisions. If we are on 1, if we chose 1 to be placed in the slot, we have passed all of 0. 0 is behind us. That's not going to be on our next permutation planting. We need to consider what is the next item that we plant here. So these are the items left to us that were cut out of our decision space. So we have a 1, 3, 4, and a 5. And notice our 1 is the item that was chosen. So the next item to take 1's position, the position right before the strictly decreasing section, the item is the next greatest item to the right of 1. What is the next greatest item? The next greatest item is 3. So we look for the item that is the next greatest item in the decreasing section. We look for 3 because guess what? 3 is next up in line to get the placement at this slot. and then 4 will get a placement, and then 5. So what we do is we swap these items. We swap the 1 and a 3 so that 3 gets its placement. It is next. Okay, so now we've almost completely simulated going to the next permutation. We've swapped the next routing before the decreasing section. But notice that this is on the last permutation if we were going to plans at 3. So what we need to do is turn this strictly decreasing section into an increasing section so we are on the first permutation of planting at 3. This would be the last permutation planting at 3. We want to be at the first permutation planting at 3, so we reverse this sublist. We don't need to sort it, we can just reverse it because it's already in reverse sorted order. And so now, this is how we find the next permutation. Notice we've only done linear time operations. We're not going into factorial time complexity. We've been able to use case analysis to stay linear in how we solve the problem. So 3 got its next routing and the suffix has been minimized. When it is decreasing, it is maximized. It is on the end of itself. But when it is increasing, then we have minimized this, we have minimized the routing, and guess what? This is the next permutation, and that is how you find the next permutation without using factorial time or expanding a brute force solution. And so now the time and space complexities are very straightforward. N is the length of the permutation string we start with. So the time complexity is going to be O of n. We're going to scale in a linear fashion as our input gets arbitrarily large. This is because all we do is linear time passes. We're going to do a linear time pass to find the longest decreasing sequence. We're going to do a linear time pass to reverse that sequence, and we're just going to do a constant time swapping. So none of this is going to take us past linear time. For space, we're going to stay constant. So the reason it's constant is we're just going to be using local variables, we're just going to be using pointers, we're not going to be using anything that scales our space as the input gets very large. So these are the time complexities. So if you like this video, hit the like button, subscribe to the channel. I hope this explanation was as clear as possible. This is not one of those questions that scales well to other questions. It's really one of those things where it's a raw case analysis and really understanding the backtracking of permutations to be able to analyze a solution like this. It's not something that is going to apply for many things. So that's all for this one. And